Okay, yeah, thanks for the introduction. I'm Tengyu. So I just joined Stanford last year. So this is about some of the work we have done in the last few years about reinforcement learning. So I guess I'm going to talk about model-based reinforcement learning and imitation learning. So I guess if I'm going to use two words to describe the basic idea of reinforcement learning, it's basically trials and errors. So this is a bit different from kind of like the settings that Carissa has mentioned. So here we are talking about this kind of like games or like robotics or self-driving cars where you can collect data and in a way that you want. So basically the basic idea of reinforcement learning is that you have these iterations between data collection process and the training and optimization process. So you try some strategy, right? So you want to, for example, play Go. You try some strategy and you collect some feedback, and then so this is the data you collect, and then you use this data you have got this records of games to train your strategy again. And then you improve your strategy, and you try it again with some experts, or try it again with yourself, and then you collect more data, and then you train again with the new data as well. So this is an iterative process, and the question is, how do we collect the data in the most smart way, and how do we improve our strategy based on the data we have? So the nice thing about this idea of reinforcement learning is that it does work. I guess most of you have heard of AlphaGo, AlphaZero. So for playing games, if we can play millions of games, then great. So we can solve, we can beat human actually experts. However, the kind of the questions I'm interested in right now is that what if you use these kind of reinforcement ideas for other kind of like applications besides games. For example, if you want to use it for robotics, you want to like the robotic arms to learn how to pick up objects, and or you want to use this for healthcare. If you want to use these kind of ideas to see what's the best treatment or the sequential treatments for patients. And now, for these kind of applications, the challenge turns out to be that the sample efficiency challenges. So we care about data. So we can collect data, but we cannot collect infinite amount of data for these kind of applications. So for Go's, you can play millions of games, but for robotics or healthcare, you cannot try as many times as you want, right? So for robotics, there's a physical constraints on how many trials you can let the robotics to do, and for patients, of course, you cannot let the patient try on the patients for many times. So that's the main question. And in this talk, I'm going to talk about some of the ideas we have to reduce the amount of trials in reinforcement learning. And this includes model-based reinforcement learning, which I'm going to mostly talk about, and some of other ideas like imitation learning from demonstrations or multitask reinforcement learning. So I guess there are other kind of ideas that could be potentially useful, like hierarchical learning, safe reinforcement learning, so on and so forth. So model-based reinforcement learning. What do I mean by model-based? So I guess let's go back to this kind of like a two-phase of strategy, trial and error strategy, right? So we have data collection and training optimization. So here, what we're going to do differently is that we are going to model the dynamics or the mechanisms of the world to anticipate the future. So what do I mean by that? So basically, in the data collection process, we still do almost the same thing. We try some strategy. We collect feedbacks. We know whether we win or not, or whether we succeed in our tasks. And also, we collect observations about what happens in this process, right? So and then on the right-hand side, we still improve now we are trying to learn the model of the world. So we want to learn a model to anticipate what happens if I do some actions. So this is a model that predicts what happens in the future if I do some actions. And now I'm going to optimize my policy based on anticipation of the future. So I guess just to if this sounds very abstract, then let me give you an example in a real world case. So actually, I told my wife about this algorithm a few months ago. My wife also does some work in AI, but she only knows the basics of reinforcement learning. And after I told her, she told me, okay, this algorithm is easy because it's basically like how do you plan vacation at home? How do you plan vacation? So basically, so I think suppose you want to go to Hawaii, right? So like Hawaii is one of the places that we enjoy a lot. We go to Hawaii a lot of times. So I guess the first thing you probably want to do is to plan your vacation at home, right? So you anticipate what you're going to do in Hawaii and plan, what restaurants you want to go, what activities, what's the route you want to go when you do the hiking, so on and so forth. And then you go and enjoy the trip, and then you keep notes on the good restaurants and activities, so that next time if you go to Hawaii again, you know how to explore and enjoy Hawaii much better. So in some sense, plan the vacation at home is kind of like planning based on anticipation of the future. So you are planning in the world model you are learning, you learned. And go and enjoy and explore. This is like the first step. Try the strategy and collect feedbacks and observations, and keep notes on the good restaurants and activities. This is a process to learn the world, learn the maximum of the world, so that you can use this, kind of like notes or like this learn dynamics to plan better in the future. So this is not only just trials and errors, but also you learn from the trials the dynamics of the world. So I guess what's the challenges and why we cannot make this work very well. So the challenges in deep model based reinforcement learning. Of course, by deep I really mean that you use deep networks in all of the modeling process. So the issue is that the learn dynamics may not be accurate enough for those states you haven't seen in the training trajectories. I guess this sounds a little bit abstract. So the basic idea is that you have a lot of training trajectories. You have a lot of good notes about what restaurants you have been to and what are the good activities. And for this kind of trajectories, you are very accurate. You know what will happen if you do, for example, parasailing in Hawaii. So, however, maybe the best activities you want to try, or the next activity you want to try, is something different from what you have done before. So, if you predict the future, for this kind of activities, you can be very accurate. But if you do something different, for example, now at home you predict that you anticipate you are going to do some other activities like hiking, then maybe because you haven't been hiking at Hawaii, so you are not going to have very good predictions about what will happen with hiking. So then the predictions for the future is going to be not very accurate. So how do we solve this issue? So the classical idea to solve this is you have this so-called exploitation and exploration trade-off. So by exploitation, what we mean is that you only go to those places you have been to. So you only go to those restaurants or activities you have been to so that you can be accurate about what will happen with those activities. So then, of course, you are not going to have any surprises, but however, you are not going to explore new activities. So you're going to miss some interesting places, for example. And exploitation is that you want to improve your certainty of your model by trying some diverse policies. So by trying something new about new restaurants, new activities, and then of course the problem with this is that you may try something different. Of course you are going to learn the world better, but you are not going to necessarily enjoy much because you may try something you don't like. So the main idea, the main kind of challenge in deep reinforcement, in reinforcement learning is that how do you balance the exploitation and exploration? And this is particularly challenging for deep reinforcement learning because we are going to use neural networks, for all of this. And then how do you measure the certainty of your model? How do you know when you are certain, when you are not certain, so on and so forth? This becomes challenging. And just to add more kind of like subtleties in the picture. So mention some more subtleties in the picture. So actually, when you do deep reinforcement learning, sometimes another challenge is that the accuracy requirements for your predicting the world are not uniformly spread over the space. So for example, suppose you imagine that you have a robot and you are walking, on the top of the mountain, and this robot, observes the world and anticipates what will happen, if it, walks to the left or walk to the right. So, however, your prediction of the world or your understanding about the world has to be very, very accurate if you walk to the right. right? So because if you are making a little bit mistakes about what will happen next, then you may fall off the cliff. But if you walk to the left, then it's kind of more relaxed, right? So it's not really necessary to learn the world that accurately. It doesn't really matter what exactly the slope it will be, as long as it's relatively flat, it's probably fine. So the accuracies requirement are not uniformly distributed. So this just gives you more subtleties about how do you measure the uncertainty of your model across the space. So I guess I don't have much time, so I wouldn't tell you a lot of details. How do we address all of these issues? But the basic idea is that you want to kind of like be very fine-grained about what you should do for every place under different kind of uncertainty. I'm going to show you some kind of like quick results. So we have some new algorithms that is inspired by theoretical analysis. I'm partly a theoretician, so we use mathematical derivations to figure out what's the right way to do based on your uncertainty measure at different places, and we provide guarantees, and these guarantees inspired algorithms that can perform better than the previous algorithm. For example, we have this paper that appears in this year's iClear, which outperforms prior works when 1 million or fewer samples are permitted. So here are some kind of demos which further demonstrates the idea. So this is some demo about how to learn a humanoid in this environment. So recall that we are going to build a model for the world, and a model for the dynamics to anticipate the future. So on the left-hand side, I'm going to visualize what the humanoid will behave in the anticipation, in the imagination. So this is like what the humanoid kind of imagines it's gonna do, and on the right-hand side, we're going to see what the humanoid does in reality. So I have like an iteration number here. So at iteration 10, our model is not trained very well. So you can see that this is what the humanoid anticipates. And this is what the humanoid really does in practice. And you can see that the model to anticipate the future, to predict the future, is not very accurate, because after a few steps, the prediction is pretty wrong. And at iteration 20, the same thing happens. You can see that after a while, the prediction for the future becomes off, and actually we're not using any prior knowledge, so you can see that when there are not enough data, the prediction for the future could be even invalid. The food is actually under the ground, so this is actually not even a valid prediction. So, however, just fast forward after 200 iterations of training, you can see that what the humanoid anticipate in the future in the learned dynamics is very accurate, and the policy learned is also simultaneously much better. All right, so I guess we also have some later results, and which further improve the sample efficiency. And now I think the kind of the status of the research is that for this kind of humanoid environments where there are like 100-dimensional states and a lot of control actions, like 20 control actions. So for even this kind of very complex environments, you only require about 200 trials, each of length 1,000. To solve these tasks. You only need a humanoid to try 200 times to learn how to walk to the right. And in the last few years, I think a lot of these papers, including some of ours, so collectively, I think these papers improve the sample efficiency by at least a 10x, but depending on how you compare, 10 to 100x fewer samples compared to even 2 years ago. So this is a very fast-moving area of research. I guess I'll spend the next 2 minutes to briefly talk about what happens if you want to be even more kind of like aggressive or greedy about the sample efficiency. So what if in certain cases you don't even have the resources to try for 200 trials? 200 trials already sounds like pretty impressive, pretty small. But what if you just you can just only try, for example, 5 times or 10 times? So these are some ideas, an idea called imitation learning, or learning from demonstrations. So we kind of like think that in certain cases RL from scratch may not still be sample efficient enough. And then for imitation learning, the idea is that we are leveraging additional data from the experts. So the basic idea, if we are still use the Hawaii or the travel example, so basically you are given additional information from some experts. So you are reading some kind of like a travel guidebook. And this guidebook will tell you how to do things much more efficiently. Of course, the guidebook wouldn't be itself enough, because even if you have the guidebook, you may still have the issue that you follow the guidebook, for a few steps, and then you kind of like you're you cannot follow anymore, because because the guidebook is very particular, and you didn't follow exactly all the previous steps, and then you cannot follow anymore. So this is the main issue of imitation learning that we try to resolve. So I guess just to briefly talk about this, using a picture. So the guidelines or the experts tells you how to go to the goal with this kind of trajectories. However, when you really execute it, you make some error, and the error can cascade. So the first step, we make some small error, and after a few steps, the error becomes bigger and bigger, and then we cannot follow the expert. So this is the problem with this classical algorithm called behavior cloning, and we have some ways to fix this by saying how do we kind of correct ourselves to get closer to how the expert does. So I guess I have 1 minute. I will just briefly wrap up. So I've talked about how do we improve sample efficiency of reinforcement learning using the idea of model-based reinforcement learning or imitation learning. Looking ahead, I guess the open questions include, of course, for both of these, directions, still there are a lot of technical work to be done to further improve the sample efficiency. But broadly speaking, looking ahead, I guess safe reinforcement learning and multitask reinforcement learning are another two directions. I personally are very interested. I think they are very excited because in many cases, for example, in healthcare, you can do some trials and errors, but you want the trials to be relatively safe. You don't want the trials to be too bad for the patients. And also you want to learn a lot of policies together, like a lot of different policies for example, patients or different robots together. So this is multitask reinforcement learning. I guess, generally speaking, how do we improve the sample efficiencies for other applications, for example, healthcare? That's all I want to say. Thank you.
Yeah, short question with regard to incorporating, say, previous knowledge about good or bad actions. Maybe it's related to safe reinforcement learning. But I have 3 daughters, and everybody knows that from educating somebody. You have some previous knowledge from parents to say, don't do that. It's already, it doesn't need to be learned. Or it could be learned because kids try out different things and come to different conclusions on their own. But are there similar thoughts in the reinforcement learning space? Because I think it's very similar to how humans learn by experimenting, trying what's working, what's not. But the way to accelerate that as human is that you incorporate what's already known as good or bad action, basically.
Yeah. So I guess imitation learning. Thanks for the question. So imitation learning is part of this. It's kind of like this idea. So the knowledge are from some experts. Of course, I guess probably you are also referring to other experiences that the agent or the like we have before, not necessarily expert policy, but some bad experiences or like good experiences. I think this is an area called off-policy reinforcement learning, which means that you have a lot of existing data. So this data may not be expert policy. So some of the trials are not successful, but you don't have a lot of possibility to interact with the environment in the future. So you want to learn as much as possible from the previous experiences. I guess the general problem is similar to imitation learning. So the problem is that you may deviate from what you have seen before because because you want to do something better than before, right? So you have to deviate, and when you deviate, you are not sure about what will happen. So there's a balance between how much you want to deviate from the previous experience and how much you want to learn from the previous experiences.